Welcome to our lecture on cloud computing. Yesterday we had the test exam and many actually participated in the on-site, so thanks for that. We were able to test our screen recording software. Everything worked except a few cases that need a bit of help, but otherwise it looks good. So, today I will be talking about the Internet of Things, and it's quite related to the cloud. So you will see that there are different types of architectures for the Internet of Things, and so they are all cloud-based basically. No? And yeah, then we have also the last exercise for you, the FAST exercise. And then next week we will have the guest presentation, and on Wednesday and on Friday we have our exam. Good. So let me start. What is the Internet of Things? Probably you all have an idea about that. So it's a system of interrelated computing devices, mechanical and digital machines, objects, animals, people that are provided with unique identifiers and the ability to transfer data over a network without requiring human to human or human to computer interaction. So we connect objects to the internet, and they can communicate through that. So you can think of cars, for example, machines, production machines. You can think about sensors, actuators. You can think of wearables, for example, that persons actually have devices like a smartwatch or some sensors on the clothes that actually communicate with the outside world through the network. And this is a very important aspect of today's development. So we get more and more data about the environment and can optimize our usage. So the Internet of Things, when did it start? And there is a definition from Cisco. They defined that it started when the number of devices connected to the internet exceeded the number of people on Earth. And so basically that is here between 2007 or so. Between 2008 and 2009, when we passed, the world population went up from 6.3 billion to 6.8 billion, and the number of connected devices went up from 500 million to 12 billion devices. And this is constantly going and exponentially increasing the number of devices connected to the internet. So you might want to have a look at the publication down here that is mentioned where they describe this. So what are these devices that are connected to the internet? So these are obviously, first of all, sensors, that you measure temperature, you measure water depth, you can measure oxygen level, and so on and so on. All these sensors are part of that. Then we have the so-called actuators. That is, these are devices that can actually react to a command from the internet and do some change. That could be, for example, a robot that starts to deliver pizza to your home, or it could be the switching on of your electric car, so where the battery is then loaded when there is enough electrical energy available, and other examples you will find easily. There are consumer devices. Coffee machine can be sensed what the status is, but you can also start preparing the coffee in the morning. Industrial machines like 3D printers would be a nice example, right? So maybe those of you having experience with 3D printers know that it's first of all, it takes quite a bit of time to print something, right? And second, there is always a danger that the print will not be what you expected, that you get some spaghetti or so. And so it would be nice that, for example, you observe with a camera or some other sensors what's going on the 3D printer, and you are informed early in time, not only when you wake up in the morning, that something is going wrong with the printing of your model, right? So variables, e-scooters, cars, planes, buildings, and so on, all these are devices that will be connected to the internet. So what are the applications? So we can think of consumer application, a very famous smart home, no? That you automate your home. You switch on the light bulbs by command to Siri. You can see what the temperature is. That might be important in the winter, coming winter when we run out of gas. Or whatever, yeah, you can open the door automatically once your sender at the door found out that this is a person that is authorized to go in. Clearly, elder care is an important area. So to actually observe what the elder people are doing at home and maybe be alarmed if something went wrong, some health problem is there, or they cannot, they don't stand up from bed, or so that people can observe this and can start taking measures against it. There is obviously autonomous driving, an important area, so that our cars, hopefully at some point in time, maybe a bit far away, are able to drive us through the city of Munich, and they need a lot of information to do so. Commercial applications, healthcare, obviously, to gather data about the health of the patients, whether medicaments are taken, and so on. Transportation, clearly optimize maybe the public transport, as well as building automation, so big public buildings to manage them automatically. Industrial, manufacturing, and agriculture. Agriculture is also, maybe you heard about precision agriculture, so where actually, the herbicides, is it? So are actually placed at the right only if necessary, or you can imagine that you have projects like robots going through plants for apples and detecting whether the apples are okay or not, and they will inform the owner to actually take measures if it's not the case. Then infrastructure, smart city, energy management, environmental monitoring, all these are applications in that field. So I would like to come now to the IoT architectures, and there are three architectures that I want to talk about. The first one is the IoT Cloud. Then we talk about IoT Edge architecture, and then IoT Fork. So let's start with the IoT Cloud. So that is basically following this design here. So we have our IoT devices here, and these are little microcontrollers equipped with communication facilities, and you can basically put sensors there or use them to signal something to an actuator. And these devices are then connected through a gateway to the internet, the wide area network, and they are connected to the cloud. And in the cloud, you have what is called an IoT platform, which basically would allow to store sensor values, to process the sensor values, to train models, for example, for prediction, and so on. So that is a very classical architecture here, where basically the devices communicate directly with the platform in the cloud. So what is typical, we have wired or wireless connection to the sensors and actuators to the gateway, and I think most frequently you actually have wireless communication between the sensors and the gateway. Then we have sensor data. They are forwarded, as I said, to the IoT platform, which is in the cloud, and the platform itself offers then scalable services. So, for example, to store the data as well as computation. And you can imagine that scalability is a very important aspect if you think about the number of devices that we have. Yeah, this is definitely something that is absolutely required. So then, you can imagine that, for example, processing capabilities are needed, that there are triggering actions to do a prediction or to train a machine learning model. These triggers can be, maybe come from the data, so that actually there is a rule that says, okay, if this value is at a certain level, then I actually have to do something. Or it can be machine learning, that you actually send pictures, images from cameras, and you apply object detection, and maybe you detect a dangerous situation or so, and you want then trigger an action. No? Then there are typically also visualization services, so that you can look at the data. And obviously, you also need support for data retrieval. Maybe you wanted to extract data from the platform for further processing or archiving or whatever. So that is the first one. The second one is the so-called edge architecture. In the edge architecture, it looks a little bit different. Not much. There is an edge computer here, right? So there will typically be a gateway, and to the gateway we have connected an edge computer. And the problem with the previous architecture is that there is quite a latency to deliver the data to the cloud, process the data in the cloud, and then send actuations back. Yeah? And so this latency, for latency critical applications, you can think of autonomous cars, for example. This is a big problem, right? And you need a much lower latency, and you can achieve this only by processing the data near to the gateway, right? And therefore, the term edge computing was introduced. It is at the edge of the internet, and so directly where the data arrive, we process them and can trigger actions from there. So it's low latency. Nevertheless, there is still the connection to the cloud, to the IoT platform here, to store data and do more compute-intensive stuff. And there is a second reason for these edge systems, that we can expect that actually the bandwidth limitation in the communication between the gateway and the cloud would actually become a problem. Think about streaming a lot videos from cameras. So then if you continuously stream, you need quite some bandwidth to the cloud. It would be much better if you have a system that can actually pre-process these videos, identify interesting scenes or important scenes, and only forward these important information to the cloud. So by that, we reduce the bandwidth requirement between the gateway and the cloud. So these are the two things that are always mentioned as motivation for using edge systems. So there is also quite a bit of variation in if you talk to people about what an edge system is. So it's considered, I think we all agree that these edge systems are not full servers. So it's not a big server with that you find at LRZ or so, but these are smaller machines. And so at our share, we actually have a board, a wooden board with 6 different what we call edge systems on there. So these are Raspberry Pis, for example, Google Dev Board, Jetson Nano, something like that. So smaller mini computers, but still much more powerful than microcontrollers that are used in the sensors. No? So that is, I think a good design, because you could run, for example, a neural network inferencing you could run on the edge system, but you cannot run it on the microcontroller simply by the limited resources that are actually there. And so recently I learned that actually really an important argument for these edge systems is that they are passively cooled. So there are no fans in there. The idea is that these edge systems are distributed and you don't have lots of maintenance to do. Yeah, as soon as you have a fan, this is seen in industry to be a problem, right? So it's highly likely that a fan breaks, and so you need passively cooled systems. So, and I got that is the viewpoint of actually a few companies that I talked to in the last months, and I think that is a valid argument. No? And these edge systems would be distributed, for example, in plants. So think about the plant where BMW produces cars. Yeah, so instead of sending all the sensors from this big fabrication hall to the cloud, you actually send it to an edge system where you can already pre-process it. Yeah, and these edge systems have to be very reliable and therefore no fan. No? Right. There is one more aspect about this edge, and people discuss heavily about the interest of the telecommunication industry to put such edge systems into the base stations. So the base stations that offer GSM, no? So why to put it there? Because you can then offload applications from third parties to these servers, and they can directly communicate with this mobile device that sends data. It can take decisions, send information back, and you don't have this long delay to go to the cloud. Yeah, and that is something that is, if you talk to Telecom or so, or Vodafone, and that is something that is definitely on their plan to do and to offer. I'm not aware that you already can dynamically send services to these guys and handle your customers or so there, but that is, I think, something that will definitely come. So, edge computing, the computation and data are shifted to computers at the edge of the network. It extends a centralized cloud model into a distributed model. We have now distributed systems there, for processing the data, and the intention is to bring computation and storage closer to the location where it is needed to improve the response time and save bandwidth. So, typically, you have specific applications in fixed locations. So you have, I think the current status is that these edge systems are owned, for example, by the company, and they determine which application is running there. It's not like a cloud model where you can dynamically migrate applications to these edge systems. So here are a number of examples for such an edge architecture. And finally, we have the third one, which is the IoT Fork Architecture. So it's an extension of the edge. So we still have, here our gateways here. But we not have only one edge system, but we have actually a sort of set of servers. And these servers provide now more compute power already in a distributed fashion before the data go to the cloud. So we can look at it as an extension of edge computing, where you have these edge systems which are directly at the gateways, and beyond the edge system, you directly communicate with the cloud. So now we have in between also these additional systems. And here the first bullet point says it's an extension of edge computing. It's a use of coupled edge systems for adaptivity. So think about that you have just our first, in the edge architecture, our edge systems that is connected to the gateway and can do some computation. So now we couple these edge systems so that there can be communication between. Yeah, usage of service might migrate between different edge systems. Why might we want to do that? Think about cars moving around. So the car is depending on the location where it is connected to a certain edge system, but maybe some processing is still going on, and so you need to communicate to the edge system it's now connected to. So this is the first way. Yeah, we can look at this fork as being extension of this classical edge architecture. And the second one is we can replace the cloud with the edge. So we actually push cloud functionality here into this intermediate space with additional servers. And what is important is that these servers are location aware. They know where they are and can consider this in their collaboration to solve a certain application. So this is shown here in the picture. So these are basically our sensors and actuators. And then part of the cloud are the let's say, classical edge systems here. And then there is a network of servers that can actually do additional processing. And we can imagine that you could use such a hierarchy to propagate information from an individual edge system to a server which is responsible for a larger region, for example, and provide processing of requests that actually come through different edge systems in that region based on all the information that it got from the different edge systems. Yeah, think about a smart city, for example. Yeah, so we have in Munich, let's say we have a number of edge systems. What would it mean? Maybe on the campus we have 3-4 edge systems for the different areas. Then you have over the entire city, you have hundreds or thousands of edge systems, and the processing that is required for the interaction of the devices with this infrastructure would actually be done in a region aware, local servers that are sort of in a certain region. Yeah? Think about RBG, they would actually receive all the requests through the edge systems and provide a more global view of the data from the campus here. So, right, so this diagram shows that the higher we go, actually the latency increases. Yeah, so here in the sensor we get the data. It would be the shortest latency that we get to react to sensor values. Then the next level would be this fork layer, where we have the edge systems, and then there is obviously a longer latency to go to another server and receive commands from there. And the longest latency would be to go to the cloud and process the information in the cloud. So that is this side, the latency, and here on that side we see the number of devices. So the cloud is only tens. Here we might have thousands, and here we definitely have millions of devices of edge sensors and actuators there. Good. There are also people talking even about mist computing and so on. But I think this term fork computing is definitely sort of relevant because we go more in a distributed architecture, and for all these applications that will process the data coming from the sensors, we definitely need distributed processing. Good. Here is a definition of fork computing from NIST, and we looked at the definition of cloud computing, so I looked it up for fork computing as well. Fork computing is a layered model for enabling ubiquitous access to a shared continuum of scalable computing resources. The model facilitates the deployment of distributed, latency-aware applications and services, and consists of fork nodes residing between smart end devices and centralized services, so between our sensors and actuators and the cloud. The fork node is a core component of fork computing architecture. Fork nodes are either physical components or virtual ones that are tightly coupled with smart end devices and access networks and provide computing resources to these devices. The fork nodes are geographically distributed, and they is aware, they are aware of their distribution, geographical distribution, and the logical location within the context of its cluster. So it knows how far away other fork servers are, and it would take this into account, or you can take this into account. Yeah, that is important that you have this location awareness. To deploy a given fork computing capability, fork nodes operate in a centralized or decentralized manner and can be configured as standalone fork nodes that communicate among them to deliver the service, or can be federated to form clusters that provide horizontal scalability over dispersed geolocations through mirroring or extension mechanisms. So I think what they actually say here is that you can think of that you have individual fork nodes that are connected to certain edge devices. Yeah, and you can use them in a hierarchical fashion to process the data. But obviously, we also want to have this fork layer to be federated, that actually these is a shared resource. And you can actually migrate computation and data between different of these devices in the fork layer. Yeah? And then it becomes a sort of cloud. Yeah? So on demand, you can allocate some computation, some resources in the fork layer, and do some computation there. So these are the essential characteristics. So it's first the location awareness. So as I said, they know which servers are actually near and would place, for example, computation only on a near server and not on a far away server in the fork. Then there is a geographical distribution. There is heterogeneity, so with respect to the data, and there is interoperability and federation, so these servers should work together. That is, here's as an example, given real-time streaming requires cooperating between different providers. Fork components must be able to interoperate and enable federated services across the domains. Right, and then real-time interaction. So it is for real-time interactive work and not for batch processing. So processing a large set of data will still be done in the cloud. Scalability and agility of federated fork node clusters. As I said, the ideal situation is that you look at this infrastructure as like a cloud, right? So you have lots of servers there, and you can dynamically use the servers, and you have this awareness of the latency and the geographical distribution there. So there are different fork computing service models, and so we can imagine that this is more an infrastructure as a service, that basically the providers would allow you to allocate a virtual machine on such a fork device, and then you can do whatever you want there, right? We could also think of platform as a service. So let's say we have a function as a service offer across these devices in the fork, right? And then the distribution of the triggered function will be done automatically. No, that would be a platform. We could think of that it's a Kubernetes cluster. So on each of these fork nodes, it's basically a Kubernetes node, and then you distribute the pods across those guys, right? And we can also think of software as a service, that basically the provider that distributes the resources actually provides also high-level applications for managing your IoT needs, no? So you see that the fork layer, and I think that's really something that you should understand, is thought of being a layer where you can dynamically allocate resources and handle, as in the cloud, which is centralized. No? These are data centers here. These are different distributed servers. location awareness is there, and but they are managed in a cloud-like fashion on demand. Okay, so deployment model, private fork nodes, that is probably at the moment the most common one that organizations set up some fork nodes. You can think of community fork nodes, public fork nodes, and hybrid fork nodes. So they basically extended these definitions from the cloud to the fork layer. Good. Let's come back a bit to that here. I thought it might be interesting that you come up with examples. So maybe you can think of why, what is better, why, for which use cases would we use the cloud architecture, the edge architecture, or the fork architecture? Maybe someone wants to put in some ideas here. Yeah.
For like power, like applications that are low power, maybe a cloud IoT would be good, because then you don't need like a power hungry GPU as a edge.
Yeah. Okay, a good point. Yeah, so if you have an application or you have an environment, let's say, where you cannot plug in these fork servers into the power grid, yeah, you really have to run it from battery. So maybe then it's better to move computation to the cloud. Yeah, that would be one reason to go for the cloud. Yeah.
Maybe an example for edge architecture would be if you have an Alexa at your home, then that would be an edge computer that controls all the sensors for maybe your LEDs, and then you have like an edge computer that doesn't need ventilator.
Yeah. And you have the advantage that maybe you can keep this local, right? So I think the current Alexa always talks to the cloud, right? But that is something that many people might not be happy about, no? So it has a privacy aspect as well. Yeah, yeah, right. And it's really something that is local, a local service, and so that would argue to do it in a distributed fashion, right? It's nothing that requires central computation, no? Yeah. Other ideas? What about autonomous cars? That is also something I think is a nice context. What do you think we could do with yeah? So how does
I think autonomous cars need really low latency.
Yeah.
And therefore, and maybe they don't have the processing power in the car themselves, like the fully processing power of all the sensors. And maybe they just get the information from some servers that are close by, but not in the cloud entirely. Some kind of edge in the city or something.
Yeah. So there might be an overload of the IT system on board, no? And so you might offload some computation to the edge, no? That is one aspect that you mentioned. But probably these cars could profit also from information from other cars, right? And this can be done in two ways. What is the most probable way to do it? What the companies are all working on? Car-to-car communication, right? No, that is, I think, all all companies have their, maybe even their own protocol or hardware for that. Yeah. So the idea is that the car in front of you can actually inform you about there is a traffic jam, please brake, right? Don't crash into me. No? So that is vehicle to vehicle or car to car communication. But I could also imagine that there are other services that are not that near. Yeah, this vehicle to vehicle communication is probably for instant communication, right?
Question to that.
Yeah.
Wouldn't car-to-car or vehicle-to-vehicle communication not also be like edge? Like,
Yeah.
you would get
Yeah.
information from another like fixed location environment.
Yeah, we could also look at the computation in the car as being a sort of moving edge system, right? Yeah, obviously, yeah. These definitions are not that precise. Yeah, typically you think about a piece of hardware that is at a fixed location, but it's not necessary. Yeah.
I would say for the aftermarket.
For?
For the aftermarket, so basically the cars can maybe send data to the manufacturer to the OEM, and then they can use machine learning and detect whether you should replace a wheel.
Predictive maintenance or so, no? That would be.
The owner come back to OEM and can need something to be replaced, for example.
Right, yes. Or I could imagine that, yeah, these edge systems actually keep track of dangerous situations. That there is a truck coming high speed on one of the roads, and so it would actually know about that and could communicate this to others, right? So that it's not a vehicle to vehicle. Maybe there is no vehicle in front of that, and it could detect it with much more time until a crash might happen. No? Or my favorite example is also searching for a parking lot. So we all know that you have to drive around your quarter and you want to place your car, you go around and you search, and then almost you had a parking lot, right? But another one was before you. So I think that would also be a typical example, yeah? So we need an edge system which basically keeps track of information where free spaces are, and you contact it and it tells you, oh, go into this street and you will find a space that is large enough for your car, right? So that is my favorite thing I would like to have. Okay, and yeah, these autonomous cars, I think, is also a good argument to not send everything to the cloud, because as one of you said, no, it's latency critical many times. No? Other services are not that critical, so maybe my parking service actually has enough time there to get information to not have it necessarily on the edge. But maybe the bandwidth reduction could be an interesting aspect. No? Yeah. Okay, good. So another topic for IoT are IoT networks. And these are actually used to connect the devices to the gateway. So here we have not the classical internet connection, but there are specialized networks that are used for the connection between the devices and your IoT infrastructure. And an IoT network is typically a wireless network, and it connects sensors and actuators to the gateway, and the gateway is then responsible to forward this to cloud or edge system. No? So there is another term, so IoT network, there is another term called sensor network. So the term sensor network is used for situations where actually not all the sensors have a direct connection to the gateway. Yeah, and you can imagine that this happens in rural areas, right? You distribute sensors over a big space, and simply the gateway is too far away. And so sensor networks is a term that is used that actually the sensors communicate between each other, and by that allow further distant sensors to actually reach the gateway. Yeah? So it's a network that is basically installed there by the sensors itself. And that is, I think, for rural areas very important, no? So to have such features here. Good. Yeah, these are use cases for IoT network technology. So smart grid parking, smart traffic, smart home and building down here. Yeah, you distribute your sensors, and you want to actually collect the information from any points, and those that have some smart home appliances at home know that these work wireless, to some gateway or to your Wi-Fi gateway. Right, so then we have for smart administration, smart health, obviously, lots of Wi-Fi or wireless enabled devices around to track patient status and so on. Good. We distinguish 3 different categories of IoT networks. There are the wireless personal area network, or WPAN. So like Bluetooth, very short distance connecting devices to to a gateway, right? There are others as well. So Bluetooth, Zigbee is one. This is typically something also for the valve control. No? These are such wireless personal area networks that are used there. They are limited, very limited in distance. Then we have the wireless local area networks that we all know, no? WLAN, and then we have the wireless wide area networks. And to that, examples for that are LoRa and LTE, so GSM communication. And down here, we see how these classes are determined. So that's communication in the range of several tens of meters. Then we have here in the range of hundreds of meters, and here then up to kilometers. And right, so for Wi-Fi actually. Inside of buildings, you are much more limited than the 100. Outside, maybe you can reach a kilometer, I don't know. But I think that is also a coarse estimation here. Good. So I'm interested in the low power wide area networks because clearly, I mean, in many places we have Wi-Fi, we can use this, we all use Bluetooth, but this is a sort of interesting area. So the idea is that you have sensors that are powered by battery distributed over a large area. And so for those, actually, these low power wide area networks are designed. And so they connect sensors over a long distance and at the same time enable a long lifetime of battery-powered sensor devices. And look at this LP1 here. So in this diagram, you can see what the strength is. It's the range, the geographical coverage because of the range, and transmission latency, but they are actually not that good. They don't need a large number of, I should say it like that, not need a large number of base stations because they are long range, right? There are maybe low subscription costs. It's not like G3, 4G, 5G, where you actually have a SIM card and a contract, right? The chipset is cheap. The bandwidth, that is maybe a drawback. The bandwidth is typically low for these networks. But at an advantage, also the power consumption is low. And compare this to the power consumption here for the GSM networks. It's much lower. And if you think about battery-powered devices, you definitely want to go for a communication technology that is low power, right? Low power and long range. That is really the interesting thing here. So, here as a comparison, we also have this near communication networks, the Zigbee or Bluetooth here. Good. So, I would like to talk a little bit about LoRaWAN as one of these networks. So that means long-range wide area network, and it's on the LoRa is basically defines the physical layer, so how the communication between two devices on the physical level is handled, and LoRaWAN determines then the medium access layer. So it's a low-power wireless communication technique for long distances, 10 kilometers in rural areas. Actually, we were able to do tests here on the campus, and we could easily reach to Freising with that, right? So I think we can confirm these kilometer distances, and there are also stories about reaching much further. So you can also use it inside buildings because it's a low frequency radio, and so it propagates much easier through walls than Wi-Fi, for example. And it's based on the approach to trade communication bandwidth for low power and long range. So that was, if you remember from the previous diagram, so bandwidth is low, but therefore you can reach a long range and it does not take a lot of power. So it's suited for transfer of messages of a few bytes because it's low bandwidth, but you definitely cannot use LoRa for streaming videos or even send pictures. So that is, I think, out of discussion to do that. So it's used in IoT infrastructures. So this is a picture that shows how the typical LoRaWAN network is organized. So you have your LoRaWAN gateways here. These are the sensors, and the gateway basically allows to communicate with the sensor via LoRa. And then you have a sort of network level organization that is here in my presentation, the Things network. It's an open network, but also the telecom providers nowadays support LoRaWAN as a communication infrastructure. And from there, the data then propagated to your application. Yeah? And what can happen in this diagram that actually you have LoRa nodes here that send messages and the message is received by multiple gateways. So it can happen that actually there is a duplication of messages, and it's the responsibility of the network server to deduplicate this, not to remove the duplicates because of reaching to multiple of these gateways. So that is the organization of LoRa. So LoRa basically is this lower part. It's a physical layer, and that is owned by Semtech. And it's based on the free frequencies. Here in Europe, it's 868, and mainly this. And in the US, you have 915. And so basically in every area, you have such a free network that is used for many different devices or purposes. So what is important is this LoRa modulation, and we will learn about this in a minute. On top of that, we have the LoRaWAN, so the medium access control here, and that is defined by the so-called LoRa Alliance. And for example, it defines different classes of devices with different capabilities for receiving information. Sending is not the problem, receiving is a critical part here. So let me show you this. LoRa is based on the chirp spread spectrum modulation, and it uses these three frequencies, 868 megahertz in Germany. And there are these three different types that I showed you in the LoRaWAN layer there. It's Class A, and the Class A device can communicate to the gateway, and after sending a message to the gateway, it waits at 2 time slots for an answer. So that in these time slots, when sending a message to the gateway, in these 2 time slots, and this is, let's say, after, I don't know, half a second and a second or 2 seconds, it will be waiting for an answer. Otherwise, you can switch off the LoRa. It will never wait for any information from the gateway. So if you want to send data to your LoRa device, you actually have to communicate it to the gateway, and the gateway has to wait until a message comes from the device, and then in the next 2 periods, it can actually send the information to the device. That is Class A. There is a Class B device which allows a predetermined point in time for communication, and then it waits for for messages from the gateway. And the Class C devices are basically permanently in receive state. But obviously, with respect to power, we want to go for Class A, right? Maybe Class B also works. Yeah, you just have to wake up your device at the right time to wait whether there is a message coming for you. So I have a little video that explains.
A plain radio signal carries no information, apart from the fact that the transmitter's been left on. The signal has to be modified in some way to be used to convey information, and there are a number of ways in which this can be done. Two of the most popular methods are to modify the amplitude and the frequency, and these will be familiar from the fronts of the traditional radio, AM and FM, amplitude and frequency modulation. Listeners to AM radio will be aware that it's more susceptible to interference from natural and man-made sources because it's not as sophisticated as FM, which is clear and resilient, and is a more complex and unnatural waveform. AM and FM will be easily recognised because of their widespread use in broadcasting. Here, we're not concerned with music and speech, but just binary ones and zeros. Digital 1 and 0 signals could be sent using AM by just keying the signal on and off. Crude but effective. With FM, one frequency could be used to represent a 1 and the second for a 0. This is also a common method and called frequency shift keying, FSK. We can see this signal jumping between its two frequencies here and recorded below in what is called a waterfall display. FSK is important as it's simple to produce and detect and is referred to in LoRa radio transmissions. But LoRa goes further and in doing so becomes more complex and even more resilient to background noise. Rather than just use the two frequencies of FSK, it sweeps between the two like this, up and down. Now, there are two parameters that may be changed on both the rising and falling signals. These are the rate at which the sweep changes, call this the sweep rate, and the range over which the sweep could change, call this the bandwidth. There are always compromises in communications, and here there are compromises in both sweep rate and bandwidth. Increasing the bandwidth provides a better quality signal, but bandwidth is at a premium. Everybody is vying for space, and bandwidth is valued and restricted. Engineering involves maximising performance using minimal resources. Bandwidths specified for LoRa are therefore restricted under international agreement to 500 kHz, 250 kHz and 125 kHz, and in Europe further restricted to just 250 kHz and 125 kHz. A slow sweep rate is easy to decode and becomes progressively more difficult the faster the change. Here's another potential trade-off. The faster the sweep rate, the more information can be passed, but the more difficult it is to accurately resolve the signal. The European system uses 6 different sweep rates, or spreading factors as they're referred to. These are referenced by numbers 7 to 12. We've already seen that LoRa devices use a lower, which is a protocol where any device can just wake up and transmit, regardless of any other existing conversations. As an alert, a device will start by sending this unique training cycle of 8 up sweeps followed by 2 down sweeps. We can break these sweeps into symbols of equal period. The block of 8 is called the preamble and followed by 2 symbols used for timing, called the synchronizing symbols. Any listening device can clearly recognize this preamble as the beginning of a packet, which alerts its attention. The transmitting device is then time limited by which it must complete the rest of its transmission. All of the data content of the packet is contained in the following symbols. Each symbol contains a discrete frequency step representing 8 bits. The data contained in each sweep is probably best shown using these examples. The details, like all good comedy, is in the timing. The best signal occurs when the endpoint and the gateway are in close proximity, but as we've seen, the attenuation increases as the distance increases. Eventually, the power of the received signal becomes unusable. This could be likened to trying to hold a conversation at a greater and greater distance. Now consider the same situation as a noisy party. The temptation is to raise your voice, but little is achieved if everybody shouts at the party. Or, in radio terms, all this does is drain the battery even more rapidly. An option would be to speak more slowly and clearly. This is what LoRaWAN does. Electronically, and it's called the spreading factor. As the distance increases, the signal is sent with the spreading factor stepping from 7 nearby to 12 at a distance. If every communication was just allowed to follow this pattern, the temptation would be for the whole network to slow down. To stop this situation from occurring, there's another rule that limits the total amount of time any transmission can take, and this is quite draconian, just 1% of the allowable time. Short-range communication, speaking rapidly, can therefore pass more data at the higher rate than the more language can do at distant extremes. This trade-off of distance against power transmitted and quantity of data sent is covered by the heading data rate that ranges from 0 to 6. 0 at the extreme and 6 nearby. Understanding this feature of LoRaWAN is quite sufficient. For completeness, I will overlay this graphic with the details used in the UK and European implementation of LoRaWAN, bitrate, and finally, receiver sensitivity. The gateway and each end device may be programmed to negotiate their optimum individual data rate based upon their local settings. This is called ADR, Adaptive Data.
Okay. So let's see. 1, 2, 3. 1, 2, 3, yeah. Okay, so we learned this chirp spectrum modulation. So you basically communicate information by having these, you communicate symbols. A symbol can be a number of bits. And what the value is actually determined how you actually go through the frequency space, right? So this one here would actually start with a low frequency, go to the high frequency. This one would start with a middle frequency, go up to high, and then continue with low. And this pattern actually identifies the information that is communicated. Yeah, so the LoRa has to detect when it starts at which frequency and continues how it processes through these frequencies in the bandwidth that is allowed. So, and you can see here, the video said that we have bandwidth of 125 kilohertz and 250 kilohertz here. And then let's say we have a spreading factor of 7 for a symbol, then this takes 512 microseconds to communicate. If we send with SF8 with the spreading factor 8, then we have 8 bits per symbol, but it takes longer because we sweep more slowly through this bandwidth, right? If we go to higher bandwidth, actually the time we need to communicate a symbol is exactly half, yeah. So, and what is interesting was also said in the video that at the beginning, when the communication between the gateway and the device happens, it actually adapts the spreading factor to the noise level. So it goes for a higher spreading factor, so slower communication if it's further away and the noise level is higher. Yeah? And by that, we can reach these long distances. So the other aspect is the occupation of the channel, right? And there are 3 subbands defined in the standard. G, G1, G2, and in the first 2 actually it's allowed to occupy it for 1% of the time, while in the last one only for 0.1% in the time. And therefore you have seen the maximum size of a message was 222 bytes. That is what you can send with a low spreading factor in that time, in 0.1 in this limit, duty cycle limit that is given there. Yeah, and 220 bytes, you can imagine you cannot send images, right? So images are definitely larger. Yeah, so you are happy if you have only 10 kilobytes or so. That is not a quality image probably. So you can forget this standard for communicating images and sending the image for inferencing to an edge system, for example. Yeah. So here, for sensors that use LoRa, I think we would actually need smart sensors that can do the inferencing by themselves, detect objects, and only send the information that an object was found, right? So, Yeah, LoRaWAN basically looks like that. We have the end nodes here. We have the gateways, and between the gateway and the end node, we have LoRa. And then we have a network server, and there is typically Ethernet between the gateways and the network server. And then you have your application servers over here. They are also connected through internet, probably, to the server. So what happens with security here? Actually, these messages are encrypted on two levels. So the first thing is that we have the application payload, and there is a key called the application session key, which is used to encrypt the data when it goes into the message that is sent over LoRa to the gateway, right? And in addition, the whole packet is also used by another encryption, the network session key here. And the network session key would actually compute this extension to the packet. So we have the header in clear text, we have the encrypted payload, and then we have also this computed value based on the network session key. And so this is only an example of a board, which is the Adafruit Feather board. It has a little microcontroller on it, which is here, and this is a LoRa communication chip, and you attach a antenna somewhere here, and so you can run it with a normal LiPo battery, for example. So just to show you a picture, the Things network, that is now the infrastructure for the LoRaWAN. It allows to enable low power devices to use long range gateways, right? So you can go to the gateways and to connect to an open source decentralized network to exchange data with applications. It's a sort of intermediate. Now, we have seen this in the previous slide, the network server. It's an intermediate between the IoT devices and your maybe platform or an MQTT server, for example, or your own applications. So it's sitting in between there. And it receives the messages from the devices, ensure integrity and security, and forward it the payload to the applications. And the Things network is actually a very nice infrastructure, open infrastructure. It's in many countries established. You can look it up in the web page. You can see a world map and see the density of the Things network. So here in Munich, you can more or less everywhere basically use LoRa-enabled devices. They can communicate to these available gateways, and you can receive wherever you want, through MQTT, for example, the payload of these devices. So you don't need an own infrastructure for that. It's free to use. So that is a very nice architecture. So it works like that. So we have the gateways here. Let me see what the time is. We have the gateway. We have a router here. And the router basically receives the messages from the gateway. It forwards the information to the broker. The broker is responsible to know where to deliver the message to which applications. So there are so-called handlers. The broker would forward the information to the handler, and the handler would actually forward it to the application. And then we have two more. It's a discovery service, so that these different components can find each other. And there is a network server which basically keeps track of the information of the keys and the devices that are actually connected via the gateway to the infrastructure. And okay. So what happens here is the gateway here, it receives the LoRa message, right? It forwards it to the router, and so the router would actually keep track of configuration for sending back messages to the device. It does protocol translation, then it's forwarded the information to the broker. the broker is responsible for deduplication to detect that the same message goes through multiple gateways to the infrastructure. We look up the device. So the devices in LoRa actually have an address which is extremely short. I think it's only 1 byte or so. So if you have more devices, this short address is not unique, and so based on this with the encryption key computed MIC component, the broker can identify exactly uniquely the device that is sending this information. There is also the frame counter check. So there is a frame counter connected frame number with each message, and if the same number appears again, then this is seen as being the danger that someone replays your messages, right? And so these messages, duplicate messages, will be removed from the network. So you basically have a unique count for each of your messages. And then it's forwarded to the handler, and the handler would do the decryption with the application key and would then deliver the message or the contents to the application. And on the other way, the application communicates to the handler, it does the encryption, and then it goes through the broker to the router to the gateway. Yeah? So you can have your own handler, so it can be in your own server, so that actually decryption of your payload is under your control, so it's not done as part of the infrastructure. But they also have these handlers available, and then the decryption is done here on the handlers that are part of the Things network. And then you can, for example, you could forward it to an MQTT server, and there you can subscribe to the topic, and you will receive the message that is sent through LoRaWAN. So that is the way we actually used it. So we had sensors that are distributed. Here on the campus, actually, there is a gateway which sits on top of LRZ, and then it goes to the Things network, and from there basically to MQTT, and then our IoT platform actually registers for the topic and receives all the information sent through this infrastructure. Good. So that brings me to the IoT platforms. I already said what the main purpose of a platform is: device management, data collection, data analysis, device control, and user management. So device management, you add, remove devices, store, edit information about devices, and so on. Then data collection, there might be different types of data that come from your sensors, can be simple types like int float, but can also be vectors of information, or could even be images, video maybe, sensor data typically are stored as a time series. So with a timestamp that the value was measured, it goes into maybe a time series database, and from there can be analyzed. And devices obviously can have multiple sensors. The data analysis, this is typically a stream analysis on the data, typically also in real time to detect, for example, anomalies or to trigger certain actuations. But it can also be a long-term analysis that you, for example, want to train a neural network that you use to predict values. That training would actually happen as a batch job, let's say, inside of the platform at certain times. It's not real time on the stream of the incoming data. No? And your device control, configure your device, update the firmware of the device, actuation in response to detected patterns that you detected a certain pattern in the stream of data and you trigger an actuation. Good. Amazon, all these big cloud providers offer such platforms. And here is an overview diagram of the AWS IoT. So basically, it starts with the device SDK, software development kit for the devices, sensors, or cars, or whatever. And with that, you can develop the code on the sensor to communicate with the device gateway, which receives the data from the sensors. And this communication is based on MQTT. Then we have here a rule engine that basically gets the stream data and would actually execute rules on that. These rules might store the data in a database, in a non-SQL database, for example, or a time series database. Amazon has all these offers, you know. Then it could also trigger, for example, a Lambda function as a service, a Lambda function when a new value arrives, and this function would actually directly process the information that arrives. No? So they have basically this rule engine to interface all the offers that they have. And then they have here what is called the device shadow. So basically, the device actually has a shadow device in this platform, and it would keep track of the status. And the application that would work with the shadow device, so it need not always be connected, for example, but it could actually retrieve the state of the device, and the device state would be automatically updated in the platform. And if there is actuation, for example, you want to influence your device, your application can do so on the shadow device, and that would automatically be propagated back to the real device, which is somewhere. So, and similar infrastructures you find everywhere. There is, what is interesting with the AWS, it was not shown on this picture, is the AWS Greengrass. That is edge computing in AWS. So, and the edge computer is used to enable local pre-processing of data. For example, execution of machine learning model. It can work without a connection to the cloud. So the Greengrass core is running on the edge device, and it can basically progress without the connection to the cloud. So if the connection is broken, it still works. And then they have means actually for communication of values to the cloud, that they are actually buffered, and then when the communication is re-established, then the information is propagated. And so you can imagine that this works with a device shadow. No? So you have a device shadow also on the edge, and this is synchronized with the device shadow in the cloud. And so when there is an interruption of the communication, the information is correctly synchronized. It allows integration with the security functions. So to make sure that you are authorized to send information from the edge to the cloud, for example. It is software running on your own hardware, so you download the software, install it on your edge system, and then it is integrated into the AWS IoT infrastructure. And it has a cloud level programming model, because it actually allows you to use function as a service. You can actually send and install functions on the edge device, which are then triggered at certain points when necessary. So it consists of three things. That is the AWS Greengrass core, which runs on the edge device. It's basically the infrastructure on the edge device to do compute, messaging, and so on. Then you have the AWS IoT device SDK. That is for the sensor device, and that is the AWS IoT Greengrass SDK. That is to write functions that can then use the features of the Greengrass core and do something with the data, for example. So that is described here, and The Greengrass SDK here actually allows Lambda functions to interact with the local services inside the Greengrass core and do the processing then. And you define this function in the AWS console, and then you say install it on the Greengrass server, Edge server there, and then it will be available for processing. So, yeah, this picture I have to show because that is our own IoT platform that we use for our lab courses. So it's basically using as a gateway here the MQTT as well. There are others, but this is MQTT that is the most frequently used one. It goes through Kafka. From Kafka, information is stored in Elasticsearch. And Elasticsearch, you have Kibana. I introduced that in the lecture to look at the information in the Elasticsearch, right? And so people can use Kibana to actually visualize the data. We have a MariaDB, which keeps track of the devices and the users. And then we have, at the back end, we use function as a service to do processing of the data. And we use it in our lab course to actually compute prediction models from the collected data, and these prediction models are then sent to an edge system for evaluation and predicting actually values. So that is what we use at the Share for our own IoT research. There are similar platforms everywhere. Yeah, so I have a small list here, and there are many more platforms available. So then a little bit of advertisement. So we run a Master Lab course that allows you to familiarize yourself with the IoT Cloud concepts, to implement a really concrete use case, and to get to use machine learning techniques for the data. So it looks like that we have equipped our seminar room with light barriers. So we actually, with the 2 light barriers, you can sense whether someone enters the room or goes out of the room. The whole thing is basically controlled by a ESP32 microcontroller that has Wi-Fi, Bluetooth on board. It's battery powered. This would basically count the number of people, and then we propagate these counts to our IoT platform. There we do the model training. A prediction model is trained with the function as a service implementation that I spoke a little bit about. We're showing you the overview picture of our IoT platform. This model is then sent to an edge computer, and in the edge computer, then the model is used to inference the number of people in 15 minutes in the room. This value is communicated to the board and visualized there. So we now have an OLED display. It's not shown here. That then visualizes the information. No? So you basically, it's really a chance from the basic data, how to collect the data, to do the modeling and the prediction part. So that's always run in summer semester now. And the other one is our bachelor sensor node lab. That is where you actually learn about the microcontroller, so how to implement sensors, what are the features, how to manage the power and all that stuff. And in the last lab, we have this board here, which now has the real boards of Cray machines here. And this, what I call the presence bar, was implemented as part of the lab. And when you walk before, and let me show you, I hope it works. Yeah, so you can walk in front of that, and basically it shows you where you are, and we want to detect that people actually are standing in front of our board. We want to know what parts of the exhibition is most interesting. So we basically communicate sector numbers to the IoT platform and can analyze this afterwards. This is based on simple ultrasound sensors here, so they can measure the distance, right? And by that, we know where the person is. So that is, I think, a quite nice outcome of our last lab course. Good. What else? Aha. So I'm at the end of my lecture. Oh, perfect in time. So I can announce next Wednesday we have our guest lecture. It will definitely be interesting. So it's Saksham Gautam from the company Netlight, and the title is Cloud 101, Building a Scalable Data Platform. Lessons learned from examples in the wild. So, and he's working since 10 years with cloud services and as a consultant now at Netlight. And he recently supported the cloud transformation of one of the largest Swiss media companies and will be presenting this case as a concrete example for the reasonings and lessons learned when building such a platform. You'll find the abstract. There will also be a teaser. It is not yet ready, but I will also put it in Moodle so that you see Saksham and get maybe nochmal a little bit more motivation to come here and listen to the presentation. There will also be a bit of infrastructure available, something to drink or eat, I guess. And so I want to invite you to come and listen to the presentation. I think it will definitely be a very nice end of our cloud lecture this semester. So maybe you go to the Moodle webpage and see the teaser later on when I publish it, and then also spread the word about